An express train moving at 160 kilometers per hour carries millions of joules of kinetic energy. Keeping it on the rails requires absolute mechanical precision. At the Bandra Terminus workshop, this responsibility falls to Kishor Chauhan, the carriage and wagon manager. His primary objective is enforcing a zero-defect running standard for long-distance consists, like the 1,923-kilometer route of the 19041 Politana Express. Kishor's operation balances two competing pressures. On the open line, his team executes rapid running repairs to maintain network punctuality. Inside the workshop, they manage exhaustive periodical overhauling to restore the fleet's structural integrity. The demands on this facility escalated with the transition away from traditional integral coach factory designs. The modern Linka Hoffman Busch, or LHB coach, extends the vehicle length to an exact 24,000 millimeters. These newer shells ride on advanced Fiat bogies, upgrading the maximum permissible operating speed of the consist to 160 kilometers per hour. The physics of a longer carriage traveling at higher speeds amplifies the vibration and stress applied to the undergear. The margin for mechanical error shrinks as the velocity scales. Safely operating this high-capacity rolling stock requires technicians to maintain tolerances measured in millimeters. A fractional deviation in the workshop can compound into a catastrophic failure on the track. Enforcing these physical tolerances requires a rigid human bureaucracy. At the zonal level, administrative authority flows from the general manager down to the principal chief mechanical engineer. Workshop policy flows from the chief workshop engineer through assistant works managers down to CNW managers like Kishor. Execution relies on the ground workforce and salary grades, stretching from Level 1 helpers to Level 7 senior section engineers who approve repairs. Kishor's career progression, specifically his promotion to assistant works manager, depends entirely on how well he optimizes the output and accuracy of this tiered workforce. Railway safety relies on a human hierarchy, where operational accountability, technical responsibility, and pay grades scale together perfectly. The pressure test for this workforce begins the moment a consist rolls into Bandra Terminus. The initial inspection happens while the train is in motion. Technicians position themselves along the platform to visually spot dangling undergear components while listening for the distinct rhythmic thud of a flat spot on a steel wheel. The second the train comes to a complete halt, a strict 20-minute countdown begins. Within this window, the team must physically touch and evaluate the temperature of every axle box along the entire length of the train to check for abnormal friction. If a technician detects a hot axle, the protocol is absolute. The component is marked, the axle box is opened for inspection, and if the heat damage is severe, the coach must be detached from the consist entirely. Time is the enemy on the open line. Taking too long delays the departure and fractures network punctuality, but rushing a heat check leaves a compromised axle on the track, risking a high-speed derailment. Inside the workshop, the visual checks of the platform are replaced by exact engineering standards. This slide shows the Schedule D3 protocol, a deep-level maintenance routine executed every 6 months, starting with comprehensive shell cleaning and roof ventilations. The bogie frame and bolster assemblies are examined for structural corrosion, requiring high-build epoxy primer touch-ups to meet MDTS 166 specifications. The tolerances here are microscopic. Technicians verify that the clearance between every single brake pad and disc surface sits strictly between 1 and 1.5 millimeters. Moving to the axle bearing instruments, earthing equipment is manually inspected to identify physical wear on slip assemblies and carbon bars. Finally, primary and secondary suspensions are audited, checking heavy-duty minor pads for microscopic cracks, structural damages, and material aging. The mechanical integrity of a 24-meter LHB coach is achieved by strictly adhering to these millimeter-precise measurements across thousands of independent microcomponents. When a component fails these checks, like a wheel set exhibiting a flat tire or heat damage, it triggers a mandatory withdrawal protocol. The tracking system relies heavily on physical analog inputs. Technicians must take a stencil and manually paint the date and the specific Bandra station code directly onto the end panel of the defective coach. Following this, a physical entry is written into the coach's maintenance card, and a formal work order is generated to dispatch the heavy part to the main workshop. This analog paperwork feeds into the metrics the PCME uses to evaluate Kishor's performance. These gauge charts track his key performance indicators. The target for en route detachments is absolute 0, alongside a mandate for flawless hot axle detection accuracy. Failing either metric triggers an immediate zonal audit. It delays the periodical overhauling timelines and directly compromises the operational readiness of the entire Western fleet. The current standard operating procedure is robust, but it relies almost entirely on human sensory perception and manual data entry. This establishes a hard, physical ceiling on how efficient the workshop can actually become. To secure his promotion to assistant works manager, Kishor cannot simply maintain the analog status quo. He must architect a predictive, technology-driven future for the Bandra facility. The benchmark for this modernization exists globally. Operators of the Japanese Shinkansen utilize high-speed automated inspection gantries to scan trains instantly as they enter yards. In Europe, networks like Deutsche Bahn have replaced physical heat checks with continuous predictive acoustic monitoring, listening for bearing failures weeks before they happen. Kishor's modernization blueprint begins by integrating Wayside Vision AI into the Indian Railways ecosystem. Instead of relying purely on a technician's eyes, trackside gantries equipped with Vision AI cameras dynamically scan the undergear, actively measuring brake pad wear and isolating structural anomalies while the train is still moving. This removes the variables of fatigue, poor lighting, or human error from the in-motion inspection process. Vision AI does not replace the Level 1 helper. It operates as an infallible filter, allowing the ground engineers to focus their time solely on confirmed mechanical issues. Inside the workshop, Kishor's blueprint replaces scaffolding and manual roof ventilator checks with automated industrial drone fleets, cutting hours off the scheduled D3 protocol. To solve the bottleneck of the 20-minute hot axle check, he proposes installing Internet of Things thermal sensors directly onto the Fiat bogies. These IoT sensors stream telemetry and heat data to the Bandra control room hours before the train actually arrives. Reactive platform checks are replaced by predictive maintenance routing. Finally, augmented reality headsets bridge the gap between analog mechanics and digital data. The precise 1 to 1.5 millimeter clearance is projected directly onto the physical brake disc in the engineer's field of view. The AR system utilizes spatial sensors to verify the physical work, refusing to digitally sign off on the maintenance card until the exact scheduled D3 tolerance is met. 100% compliance becomes hard-coded into the workflow. Kishor's proposal takes the strict engineering rigor of the Indian Railways framework and pairs it with the data velocity of global AI and IoT standards. Advancing to assistant works manager requires proving that the Bandra workshop can evolve. It means transitioning the facility from a manual operation that reacts to the wear and tear of yesterday into a data-driven nervous system that prevents the failures of tomorrow.